Okay, so in number 12, what we had this pendulum. We were going to give it some sort of initial velocity here, releasing it from a point where it was 40 degrees off of the horizontal. We had decided that the length of the pendulum was 1.25 meters. We had done a little bit of math and figured out that the height at this point was 0.292 meters, just by doing a little bit of trig. Was everybody cool with that? Yeah. Yep. All right. In A, we figured out, if we knew this velocity, we figured out what the velocity was at the bottom. In B, we figured out what this V naught had to be to get the pendulum to swing up to a horizontal point. Okay, so that was all stuff we did yesterday. So question C wants to know, what velocity do I need to give this pendulum here to get it to swing so that it gets to the top point? And not only does it get to the top point, but the rope stays taut, okay, that it doesn't go slack, okay? So our goal is to get it up to this point. So is our goal just to get it to that point? Like, do I want to make my velocity here 0? No, because if the velocity, if there was 0, then the rope wouldn't be taut, right? Okay? So there's a minimum velocity that will keep the rope from going slack. It will prevent the rope from going slack. So you guys, we learned kind of a quick super secret ninja way of doing that. You guys remember what that trick is? It's the same thing that we talked about, what velocity you have to get around a loop to prevent yourself from losing contact with the tracks. You remember, Seba?
Is it like centripetal force equals normal force?
You're warm. It has something to do with centripetal force, but in this problem, there is no normal force.
Oh, force of gravity.
Okay, there you go. Yeah, so the idea is, if you're spinning very, very quickly, then there are two downward forces, right? Gravity is pulling the bob down. That's what you call the mass at the end of a pendulum, bob. I always thought it was funny. Partly because my physics teacher was named Bob. So anyway, he looked like Abraham Lincoln. His name is Bob Logan. And so now that I'm talking about this, he used to do this thing. We used to keep track. He'd keep a thing of chapstick in his pocket, and I think on a record day, he did it 32 times, if I remember right. But he would be teaching, and he would pull the chapstick out of his pocket and take the cap off, like all with one hand. Chapstick out, cap off, chapstick on, cap back on, back in the pocket. 32 times in 1 hour one day. Anyway, Bob Logan. If you're listening out there, Mr. Logan, hi. Yes?
Really chapped lips, or did he have a fear of having chapped lips?
I don't know the answer. I never talked about it with him. I never asked him. We also always plotted, we wanted to steal his shoelaces without him noticing. We never succeeded. So.
You get someone and you tie their shoes together and you show them.
I'm sorry?
Did you attempt and not succeed, or you didn't attempt?
No, we never attempted. But we always talked about it. I know, so we failed in many ways. All right, anyway, I'm sorry. No one has ever said that. Oh, that's funny. Okay, all right, I'm sorry. I've distracted us talking about things that happened a long time ago. Okay, so before I got us off on a random tangent, Seba was saying that in order to get around the circle and maintain the tension in that rope, there are two forces pulling the bob down, right? Gravity and tension, right? And at the point when it just goes slack, what's that tension? Numerically, what's the tension at the point where it's just about to go slack? 0, right? Okay? So our goal is we want our centripetal force to be provided solely by gravity. No more, no less. Right? Which means right? Okay? So anytime you've got a problem where you're trying to keep the rope tight as your thing spins around, or you've got a car and you don't want it to leave the top of the loop, that's your deal. Okay? This comes up a lot, okay? So your m's cancel, so that means that v squared is gr, v is the square root of gr. Cool? Any questions? Okay, cool. So, to solve this thing, then we've got 2 points. We've got this initial point, and then we've got this top point up here, right? So it should be true that our total energy at this initial point equals the total energy at the top. So the total energy at the bottom consists of GPE, which is M times G times, hello?
Morning.
How are you?
I'm doing well. How are you?
I am well also, thank you. I'm a little mad that everybody didn't say, hi, Peter. Because Adams, or because what's her name? Boy, Anthony's already here.
Ray, you take me to prom.
All right. Okay, so here's my total energy at this point, right? Everybody cool with where I got those numbers? Okay, and that's got to equal our total energy at the top, right? So at the top, what's the height at the top, you guys? 2.5, right? Because we decided to make this a height of 0, and if the length of the rope is 1 1/4, then 1 1/4 plus 1 1/4 is 2.5 meters, right? So m times 9.8 times 2.5 plus 1/2 m times, I want my velocity at the top to be the square root of gr, right? So that squared is just going to be g times 1.25, right? Follow? I guess I could have put 9.8 in for g. And then solve, your masses cancel and solve for v naught. Do I still have your sheet, or did I give it back to you?
Come on. You give it back.
Okay, good. All right, everybody good with that? All right, is there, I'm sorry?
Didn't we do most of this last year?
This?
Yeah.
This problem?
Like, not that exact problem, but this
Concept. Yes, but this piece is definitely something we did not do last year.
Oh.
Last year, all the circular motion problems we did were horizontal. We didn't do anything vertical.
Oh, so you have to add that in.
Yeah, so that's definitely an extra, notch of difficulty. Yeah,
So
Dave.
when you have a car on a track and it's the same concept, you're not using FG though. You're using FT, right? Or FC because the points sort to the center of what?
Well, so in this problem, our goal was we want. So if the rope is spinning fast, then there would be 2 things contributing to your centripetal force. There'd be gravity and tension, right? But as you slow down, you need less and less force, and eventually this tension becomes 0. Cool?
Yeah.
And so that's what we did, was we just said, all right, well, we can't use tension. So we set unfortunately I erased it, but we set our centripetal force equal to gravity.
Right, but
Okay? Now, for a car on a track, it's the same thing. If you've got a car going around a loop, then if the car is going fast enough, there are 2 things contributing to the centripetal force. What are they?
well, FG and FC, but I thought you
Well,
meant
hold on.
horizontal.
Oh, I
I
gotcha.
meant that loop. I thought you meant like a track.
I see. Let me come back to that. Do you guys see that this is the same thing? What's providing my centripetal force here? Normal force and gravity, right? And so, in order to just maintain contact with the track, you set your normal force equal to 0. So once again, you end up with your centripetal force equals your gravity. Your centripetal force equals your gravity. Cool? All right. Horizontal track. What's your question on a horizontal
I
track?
thought that's what you were talking about.
I got it. So are you good? Okay. All right. Everybody good? Arande, what's up? Anthony, what's up?
Yeah, why did we do that green part again?
Here?
Yeah.
The original question was, what velocity do we need to release the bob at
Oh, got it.
so that it goes all the way around and maintains tension at the top? And so I was solving for that V naught. Solving for the V naught. You good?
Yeah.
Is everybody good? Is anybody not good? All right. So was there a 12D?
Yes.
Sorry.
Yeah. All right, I think, yeah, there was.
12D. Do the answers from A to C increase, decrease, or remain the same if the angle is increased? So that's kind of a concept-y thing. So question A was, here, so let me redraw this thing. All right, so here's what we know. So we've got bob with some V naught. Here's our theta. So question A, you were given V naught and asked for the velocity at the bottom. Okay, so assuming that that given V naught is bigger, how would increasing this angle change the velocity at the bottom? What do you guys think? If we, yeah, I mean, isn't it going to increase it, right? You're just dropping it from higher, right? So it's going to have more time to accelerate, right? In terms of energy, by lifting it higher, you're starting with more GPE, therefore more total energy, right? So you're going to have more kinetic energy at the bottom. Good? All right. Now, question B said, what does this velocity need to be to get it to come up to a horizontal point? So if I increase this angle, would that mean that I need more velocity or less velocity? Less velocity, right? And similarly for C, right? Cool? All right, so that is that. Any other questions on 12? All right, what are the ones we need to go over? Somebody, I think, Zach, you asked about number 8.
Yes, on 8-2.
On 8.2? Okay, so let me put the brakes on that for 1 second. Let's stick with 8.1 real fast. Any other questions on 8.1? Okay, and so 13 I want to do, but let's, that one is, well, you know what, let's just do it. Sure, what do you got?
I was going to say 11 also.
11 also? Okay, let's do 13. Okay, so 13, this is the first time we've seen a problem like this. So what's happening is this. So you've got this spherical ice dome with a radius of r. I think they give you a number. I'm going to solve it without the number, and then we'll put the number in later. Okay? Because I know you guys love when I do that. All right, and so the idea is you've got this kid who's sitting on the dome, and he's going to slide down. And the question wants to know, sort of how high up is he at the point where he slides off of the dome? That's him going, ah, not him vomiting, which is what it looks like. Okay, so let's do this. I think in order to solve this, we need to be thinking a little bit about what the free body diagram looks like at this point. Okay? So, so let's do that. So here's my sort of my dome, right? Here's my dude. All right? What forces are acting on him? Gravity and normal force, right? Now, so what you guys should be thinking about is this is actually an inclined plane, but the steepness of the plane is changing. You guys see that? Okay? So you don't actually have to use a derivative, but I mean, you could think about it that way if you wanted to. All right? But so what I would be thinking about is this. So you've got your force of gravity is going to be pulling down, right? Okay? Sorry, I'm trying to decide how I want to draw this. So here's my normal force. There's going to be a perpendicular component of gravity and a parallel component of gravity, right? All right, now, at the point where he leaves the little ice dome, what's true? Sure, what do you got, Peter?
Is it that the parallel component exceeds the perpendicular component?
Talk to me about why you're thinking that.
Because
Wouldn't that just happen at 45 degrees?
yeah, I mean, that's what I thought, and then I did it and I got the problem wrong. So
Okay, I gotcha. So I agree that there's definitely, these two forces are super important, all right? So let's think about why those forces are important, okay? So let me get Adam's idea, and then I want to talk about what each of those two forces are accomplishing. So what do you got?
So he would basically leave the surface when the force of gravity perpendicular is not as much as the centripetal force is needed.
Yes, I agree with that. So you just said that he's going to leave the dome when this is smaller than the centripetal force that we need.
Yeah.
I agree with that. Something else very important is true at that point. You see it, Johnny?
Would FG parallel be greater than FG perpendicular?
That was what Peter said a second ago. So I want to talk about the significance of those two here in a second. There's something else that's happening. There's something really, really important that happens at the instant he leaves the ice dome. You got it, easy?
Oh, never mind.
Oh.
All right, Evan.
That's no more normal force.
Good. He's got no more normal force. Right? Does that make sense to you guys?
Yeah.
Right? Because in order for him to be in contact with the thing, he's got to be touching it, right? And that implies that that ice dome is somehow supporting it. And as soon as he leaves it, there's no longer normal force because he's not touching the ice dome anymore, right? Okay? So the instant at which he leaves the ice dome, my drawing actually looks like this. Does that make sense? Does that make sense, you guys? This is important. This is a recurring theme. That was the same issue with getting the car around the loop, right? Your breaking point is when your normal force hits 0. Okay? All right, so let's talk about these. What you guys are saying here is a thing that hadn't occurred to me. So let's talk about what each of these two forces are doing. Okay? So what we've got is we've got him moving around a circular path, right? So in terms of circular motion, what is that perpendicular component sort of doing? Sure, you got an idea, Patrick?
Keeping it in motion.
Yeah, it's keeping it in circular motion. So this force of gravity perpendicular is changing the direction of motion. It's my centripetal force. Does that make sense? All right? And this is tangent to the motion, so that's contributing to him speeding up. So the perpendicular component of gravity is making him speed up. Sorry, I said that wrong. The parallel component of gravity is making him speed up, and the perpendicular component is making him turn. This is responsible for him changing direction. This is responsible for him changing speed. Process that for a second while I answer Zach's question.
So, just wondering, like, I don't know, I was just thinking of this and it almost seemed impossible. So could this only happen in, like, a place where there's absolutely zero friction? Or, like...
No, even if there's friction, you could do this problem if there's friction. In fact, maybe I'll put that on the midterm. It's a good question. You're welcome. No, I'm kidding. But no, you ought to be able to do that. Oh, in fact, actually, do you know what? It would be really difficult to do with friction. You could do it, but it would get ugly because as you go, your normal force changes. As your normal force changes, your friction changes, and it gets ugly. So you'd have to use some pretty substantial calculus. But this would still happen. So the issue is eventually you get to a point where your velocity is so big, like I think Peter said a little while ago, eventually you get to a point where your centripetal force is so big that this isn't enough force to provide it. Cool? All right, so are we good up to there?
And that's why when you like go too fast.
Yeah, exactly. All right, cool? All right, so, what we want to do then is we want to find the point. We want to find the height where your centripetal force is equal to your FG perpendicular. Make sense? Okay. So that is our goal. So, I guess let's talk about this thought a little bit more. So if the centripetal force is equal to Fg perpendicular, let's see. So centripetal force is equal to Fg perpendicular. So centripetal force is mv squared over r, right?
Yes.
Good?
Using a big R.
Oh, sorry. Yep, thank you. It's a big R. All right. And what about Fg perpendicular? So in general, how do we usually find Fg perpendicular, you guys?
MG cosine theta.
It's mg cosine theta, right? So what we need to do is we got to figure out where this theta is on my drawing over here. Okay? And this is going to require a little bit of geometry. Okay? So. Oh, that's not what I wanted to do. Oh. Ah! There we go. I clicked the wrong arrow. Why doesn't it want to? There we go. Okay. All right, so it. All right, so let's see. So here's R, here's R. All right, so again, if you think of this dome as an inclined plane where your incline is changing, at this instant, at the instant that I've drawn, my FG parallel points this way, right? Perpendicular to the radius, right? Or tangent to the surface of the dome, right? So I'm going to extend this line. So, sorry. So this line here represents sort of, it's the tangent. It's the direction that he's traveling at the instant that I've pictured. Does that make sense? All right, so usually when we talk about theta, we're talking about theta, right? The angle at which your incline is inclined. That's a terrible sentence. All right, does everybody see that? All right, so what does this theta have to do with my circle over here? Well, let's see. I feel like this angle in here seems important, doesn't it? Right? Like as he goes down the ramp, there's an angle that he's kind of sweeping out. So I want to know what this theta has to do with this angle over here. Or maybe it's this angle, I don't know. You guys see what I'm getting at? All right, so you guys, thoughts? Let's call this angle 1 and angle 2. Tell me something about either angle 1 or angle 2 in terms of theta. I'm going to, you all think for a minute. I'm going to be quiet for a minute. Don't shout anything out. Everybody think for a minute. Give me a thumbs up when you think you got an idea. Five or six thumbs. Okay, Maggie, you had a thumb up, yes? So what are you thinking?
Well, if you drew like a line from the center of the dome thing to the line that you.
Over here, like this, kind of horizontal it off? Is that what you mean?
Yeah. Then you can do like a little geometry and figure out that angle 2 is 90 minus theta.
Mm-hmm.
And then angle 1 plus angle 2 is 90.
Okay.
Angle 1 is theta.
Yeah, I agree with that. I think that angle 1 is theta. Look, this is a right angle here. And what Maggie was saying is if you can kind of close this angle off, here's my theta, right? So if this is 90 and this is theta, this is 90 minus theta, so this gets us back to theta again, right?
Well,
Follow?
yeah.
All right, so that seems useful. All right, so questions with that? All right, so that is one thing that I know has to be true. That's based on the forces. For him to stay in contact with the dome, this information here has to be true. Okay? Now, there's another thing that I know has to be true that has nothing to do with forces. And it has something to do with the fact that we're learning it right now in the middle of chapter 8. Get an idea, Dan?
Total energy is the same.
Total energy is the same. Do you guys agree that the total energy here is the same as the total energy at the point where he slides off the thingamajig, off the dome? Okay, so let's see if we can do that. So let's see, the total energy at the top is the same as the total energy at the point where he leaves. So my total energy at the top, let's see, it's all GPE, right? So mgr equals the total energy when he leaves. Let's see, so at this point, he's going to have two types of energy. He's going to have kinetic energy and gravitational potential energy, right? So we need to find this height. So the height at this point, and that's actually what we're trying to find, is that height, isn't it? Bless you. So let's see, so this height, are we trying to find the height or the velocity?
Right.
The height? Oh, okay, cool. Anybody see a way to find this height if we knew what theta was? If this is r and this is theta, then this height should be r cosine theta, shouldn't it? Follow? So, mg times r cosine theta, that's my height, plus my kinetic energy. Make sense or no? All right, so I've written two equations, one based on forces, one based on energy. Are there questions on what I've done so far? All right, so let's solve this mess. So I'm going to kind of consolidate. So here are the two equations I'm looking at. I'm looking at mv squared equals mg cosine theta. What happens? M's cancel. So I know that v squared over r is equal to g cosine theta. That seems like a useful thing. In this equation, my m's cancel. So now I'm looking at gr equals gr cosine theta plus 1/2 v squared. How many equations are there?
Two.
Two. How many things don't I know in those equations? Two. I don't know v or theta. Can we solve? Yeah. So here's an easy way to do it. If you rearrange this top equation, it gives you v squared equals gr cosine theta, right? So that means that gr equals gr cosine theta plus 1/2 of v squared. But v squared is gr cosine theta, right? That makes sense? So the grs cancel, and you get 1 equals cosine theta plus 1/2 of cosine theta. 1 equals, what is this, 1/2 cosine theta. So cosine of theta is 2/3. So you can find your angle and then you're done. Yes, sir.
So this difficulty level, is this representative of something that would actually be on an AP test, or is this like above or below?
I think that this is probably a little more math heavy than anything you'd see on an AP test. But, so if you just missed it, Daniel just asked, is this difficulty level like what you'd see on an AP test? Is this comparable or? So I think my answer was, I think this is more math intensive than what you'd see on an AP test. But I think conceptually speaking, being able to sort of come up with this idea that you slide off at this point is a thing that you should be able to do. Do you know what I mean?
Yeah.
So conceptually, I think this is on target. Mathematically, I think it's a little high. Does that make sense?
Yeah.
Okay. If this was an AP test, the way that they would probably do it is they'd break it up into parts. And they would say, all right, write an expression that tells me something about the force acting on the dude at the instant he slips off.
Right.
Now, write an expression that tells me something about the energy. Now solve it. You know what I mean? That I could see being an AP test question. And it's a good one because it hits a lot of things. It hits circular motion, it hits conservation of energy, it hits Newton's laws. So there's a lot going on with this problem. Cool? In fact, I may tweak this problem and do that next year. A good thought. Okay, good, you guys? All right, well, I mean, that will make the problem easier,
Okay.
right?
Oh, no, it's steps, yeah.
Yeah. All right. When do we get out? 45, is that right? All right. Shoot, we are totally tight on time. Which one was number 8? Can I look at number 8 real fast? Yep. Oh, there's no way I'm going to do that one in 5 minutes. All right. I saw a lot of people struggled with number 9 on 8-2. Yes? This one where you had the spring and the pulley and the... Honestly, I think we can do that one in 5 minutes. All right. So here we go. All right, so here we go. So this is 8.2, number 9. All right, so you've got a setup that looks like this. Is it M and 2M, is that right?
Yes.
Okay, so that's our setup. All right, so at this point, our velocity is 0. The spring, I think, is relaxed, right? So we've sort of got no energy, unless you want to consider GPE, which we're going to have to. Because the problem says you release it so that the system moves 0.9 meters, right?
Yeah.
And then blah, 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 blah. Okay? So there are 2 drawings that I actually care about. Okay, so do you guys agree that those are the 2 instants I care about? Can you see that this was supposed to be moved everything forward? Okay, yes?
The problem says that it's 2 kilograms. I don't know what the number.
I gotcha. Okay, I'm going to leave variables in just because I want to try to encourage you guys to start thinking in those terms. I think eventually I'll have to put it in. Oh, we do, because there's elastic potential energy. So, okay. All right, so yeah, so let's just put the masses in then. So this is 2 kilograms and 4 kilograms, right? So let's just do that. 2 kilograms, thank you, Daniel. 4 kilograms, 2 kilograms, 4 kilograms. All right, so this whole thing is conservation of energy. All right, so in order to solve this, we need to think about the types of energy, which KE, this is going to depend on the velocity. Elastic potential energy is going to depend on how far the spring is stretched. And gravitational potential energy is going to depend on the height. To solve this, I have to pick a point to be a height of 0. What's the obvious choice? Let's call this a height of 0. Good? All right. So in this drawing here, let's think about the types of energy we've got. The 4 kilogram thing is going to have a GPE of 0, right? And the 2 kilogram thing is going to have some amount of GPE. Agreed? But I don't know what it is because I don't know this height necessarily, right? You guys see what I mean?
Yep.
All right, so let's just call it X, whatever. There's some amount of GPE there. All right, what other kinds of energy do we have? Elastic potential energy. So my elastic potential energy is going to be 1/2, what was K in this problem? 200 times X, which is 0.9 meters, right? Does that make sense? Because if If this thing moved down 0.9 meters, then we stretched the spring 0.9 meters, right? Is it 0.09? Oh, okay. My bad. All right, hold on, you guys. We're almost done. Shh. All right, we've also got kinetic energy, which is 1/2 times what mass? All of it. 6 kilograms times v squared, right? All right, so there's my unknown. That's my goal. I want to find v. Over here in this drawing, this 4 kilogram mass is now going to have GPE, right? So it's going to be 4 kilograms times 9.8 times the height of... How far did it move down between here and here? 0.09. So how high is it here? 0.09. So that's the GPE of that. What's the GPE of this? What's the GPE of this? X. So what's the GPE of it over here? X. What's the elastic potential energy? 0. What's the kinetic energy? 0. So this plus this has got to equal this plus this. The x's cancel, solve for v. All right, I'll see you tomorrow. Finish up 8-3 for tomorrow, you guys.